continue. So we had to have a couple extra pictures here that didn't show up on our John Gille website before, but Kevin had. I think Kevin carries these around all the time. But this is showing when John Gille became an AGU Fellow, 2007. Yeah.
Showing that Kevin dressed appropriately.
This was the other AGU meeting in the summer, and he was supposed to wear a Mexican wedding shirt.
Was this in Mexico or something?
This was supposed to be a Guayabera shirt, so Kevin's got that.
I thought they were flagging.
John didn't get the
Okay, so our next speaker is Clive Rogers. We're really happy to have Clive come visit us for this. So when I first joined Clive has spent a couple of years here as a visitor.
That's not how it's meant to be. That's my notes.
Well, Clive spent a couple of years here as a visitor, and as I said, when I first kind of joined the group, Clive was a visitor during one of those years, and he gave a really nice set of lectures on retrieval theory and inverse measurements, and I went along, but it took.
How do I get rid of this stuff? I've never seen that layout before.
Oh, that's just showing the next one and then your notes.
Oh.
Yeah, it looks fine on there. So.
Oh, great.
So during these lectures, it was a series of lectures for several months, I think. And it was an hour lecture each day, and these were serious lectures. And I remember almost being overwhelmed by, because I didn't remember linear algebra, vector equations, and it took a lot of work, but it came out of it as really fundamental understanding of retrieval theory. And out of that came Clive's very famous book. Right?
That's right.
So are we going to see any equations in linear algebra?
If you look very carefully at this slide, you'll see the equations.
Okay.
Spelling of the third word.
Mm-hmm. You check it out in the Oxford English Dictionary. Of course, I mean the connection between ACD and AOPP at Oxford, the Atmospheric, Oceanic and Planetary Physics. I don't know why we've got such a long title. Most of what I say is going to be historical. I haven't done much science recently, and I'm beginning to forget what it's all about. For occasions like this, first thing you want to do is to Google the subject and see what you can find. You never know what might turn up. I don't think this was the right kind of Gille, but it's quite an appropriate thing. This one less so. I don't know if this guy is related in any way whatsoever. But anyway, looking on the web, I couldn't find any scandal at all. Unlike the occasion when I had to do a similar talk about the retiring principal of my college, Peter North, I found another Peter North who had a completely different kind of career. Don't look him up on the website here. So I went to look in my old files. The earliest thing I found about John was in 1967. This was when I was involved in the Global Atmospheric Research Program. My task was to review the state of atmospheric radiation theory and measurement for the Joint Organizing Committee. And I found in the files an ancient letter from John, who was then at Florida State, and he was making measurements of atmospheric radiation. And the next thing I found was probably the first time I met John, in 1968. We were both at the Radiation Commission meeting in Bergen. And I found a paper by John on acoustic wave propagation in a non-grey atmosphere. I've got no memory of this whatsoever. John had the misfortune of appearing in the last session on the last day, so I think we were all a bit tired by then. By 1974, I was looking for a sabbatical in an interesting place, and John was at NCAR. So I wrote to him, and he very kindly organized me to be attached to the advanced study program. And that was a really great year. I did a lot of good work. It was immensely productive, and this is a piece of my publication list, which corresponds to this period. I'm not going to tell you about all of these papers. I just want to point out two of them. One of them was my review paper on retrieval methods, which seems to have become the must-quote paper for anyone who works in this subject. It's still getting quoted. I don't know why, even though it was nearly 40 years ago. The other one, which was really a bit of fun, was that I developed a simple mapping scheme for satellite data based on Kalman filtering of wave amplitudes. And this made it easy to study waves, and it also made it easy to make movies of satellite data, which I duly did. I haven't got any to show you, I'm afraid. It would have taken a lot of effort to extract it from the film that I have. I don't have it in computer form yet. This was a time when we were both involved in satellite measurements. Oxford had been flying things since 1970 on Nimbus 4. John started in 1975 on Nimbus 6, and we both had instruments flying. Quite why I thought it was sensible to take a sabbatical at the time of a launch of a satellite, I don't really remember. But John Barnett did a very good job of looking after the data analysis while I was away. The launch was in June of 1975. When I left after that year, the group secretary presented me with some artwork based on some plots I'd thrown away. She extracted them from the waste paper basket. And this was, I was doing some analysis on the 5-day wave, which was quite an interesting topic at the time. And there's another one, a plot which obviously failed in the middle. Another place I started looking for information about John was in my collection of photographs, and I found a few items. These guys, I think, have got something to do with NCAR, I mean. This was in 1977 at the YAMAT meeting in Seattle. In 1980, there was an Ozone Commission conference in Boulder, and a large fraction of the atmospheric physics department decamped to Boulder for the meeting, and most of us stayed with Mike Coffey. I don't quite know how he managed. Do you remember how many of us stayed with you? It was most of this lot, wasn't it?
All of us were sleeping on the floor.
Yep.
With enough flagons, that worked.
Yeah, it did. Quite a lot of these people have ended up as leaders in the field. In fact, there's a few who didn't. I mean, there's a lot of coffee here. Joanna has just retired as president of the Royal Meteorological Society. I'm not sure what Howard's doing these days, but I'm sure if he was here, he'd be dressed like that. Another group photo I found was this one. I've forgotten all about this particular project. This was the Middle Atmosphere program, which has already been mentioned. This was the group doing a review of, where's my notes? Pre-map program 1, which was looking at the quality of the available data from radio sondes, rocket sondes, LiDAR, satellites, etc. And it's John, Alain Houchcorn from France, Alain O'Neill, Jim Miller from Langley, Karen Labitska from Berlin, Jim Miller where's Jim Miller from? Oh, National Weather Service. Mary's from Oxford, I'm from Oxford. Karen's also from Germany. Joe Haig, I think, wasn't part of this group, but she just happened to be there. The objective of the Middle Atmosphere program was really rather ambitious, to obtain a complete, comprehensive understanding of the structure, chemistry, and dynamics of the Middle Atmosphere. I think we're still working on that, Another thing that was going on in the 70s and 80s was a series of meetings in Williamsburg, organised by A-Deepak, the guy at the end, who was a bit of an operator, but he did some good meetings. And these really were seminal meetings in atmospheric retrieval methods. They attract small and informal. They attracted most of the people working on retrieval at the time, and they're quite influential. If you look closely, you'll see a very young John here, and quite a young Clive as well. This was another meeting in the series, 8 years later, slightly more people, but still quite a small meeting. And if you look carefully, you'll see that I've grown a beard. John seems to have developed grey hair. I'm not sure that's real. Henry Fleming's hair is not on fire. That's me trying to remove some of these black spots on it by scraping the photograph, which I shouldn't have done. I took another sabbatical in 86 to 7. I couldn't keep away from NCAR. It's a great place for sabbaticals. I've got my file store and emails from that time. It's the earliest ones I seem to have managed to save. And I found this ambitious list of what I wanted to do in my sabbatical. I managed to do 1A, 2A, and not much of the rest. A few other things intervened. I was co-opted onto the Ozone Trends panel at the time, and that was fun. That was took quite a while, quite a lot of time. And of course, URs was ramping up, and ISAMS was under development. John was Clay's co-I, and also with LIMS and LRIR data. The comparison we did between PMR and LRIR wasn't very good, and we never really tracked down we didn't resolve the differences, but it was a good exercise. Yours, you've already seen this picture, was an enormous satellite. There were 10 instruments on it. I'm not going to say anything about any of these, really. ISAMS was the Oxford one. John was working with Aidan Roche on Clays. But the UR science team was a big, happy family. It gelled pretty well, and it was great to work with. And here we are having breakfast at one of the science team meetings. This one was at the Main Dude Ranch in Bandera, Texas in 1991. Very enjoyable meeting. I believe that not long after this, the government banned meetings in places like this. Though they were probably cheaper and more efficient than meetings in big hotels in big cities. In a place like this, the people who are there just can't get away and drift away into town. They have to stay at the meeting. This is yours. It looks quite a mess. It's just covered in gold foil. You can't really tell what's what unless you look very carefully at it. And this is a few people from the science team. Dressed like this, you can't tell who's who. I can recognize myself. I can recognize Steve Werrett. Steve Massey. And I think this is John, but I'm not absolutely sure. Then I couldn't keep away. September 94, I came back for another sabbatical. And this time my main project was to write a book on retrieval methods, for which I really must thank John for giving me the opportunity to do this and a lot of encouragement. Again, I've got an awful lot of my files and emails from this time. There's far too much information. The book I didn't manage to get finished, about 3/4 done, but I had to take another sabbatical, which I did at Oxford, to finish it. URs, ISAMs, etc. were very active. There were validation workshops and all sorts of things going on. I also got involved in setting up the network for detection of stratospheric change. That was a great deal of fun, but again, it took a lot of time. I pressed the wrong button there, haven't I? The next thing was Aura, and we've seen this picture before. Some ghostly figures in the background. These are not the spirits of proposers who didn't get selected. And as you've heard, Oxford and NCAR both proposed the same instrument. So we were beaten over the head by NASA to get together and do it together. John Barnett was the Oxford PI and John was the NCAR PI. This is where the photo was taken from. I'm not quite sure what the occasion was. This is outside the Atmospheric Physics building in Oxford. And I think there are a lot of hangers-on standing around in the background.
I think the occasion was going to lunch.
Yeah, that sounds very likely. But were you taking this with you to lunch? We divided the responsibilities up between us. We did about half the hardware each. Oxford did the in-flight calibration system, the sun shield, that was keeping the sun out of the entrance aperture, and power and structural thermal system and the gyros. And NCAR did the rest. We also divided up the software between us similarly. Oxford did the ground test and the calibration data analysis, because we'd done the calibration system, of course, and we did the data analysis software for level 1 calibration, and the instrument support terminal software, and NCAR did the retrieval and the gridding and producing standard products. You've all seen this picture before. You've probably seen the model upstairs, up in FL0. Of course, it's upside down. It should be this way up. It hangs from, well, hangs is not the right word in space, but sits on the bottom of the satellite, and this is the entrance aperture. I personally didn't get much involved in hurdles, strangely. For some reason, I got involved in TESS. I'm not quite sure why, but that was nice too. I really enjoyed working with TESS. I've talked to some of these people about their own experiences. John Whitney's comments. John Whitney was a system engineer. The most enjoyable 10 years of my working life, which is quite a statement. He obviously had fun. He said people were excellent to work with everywhere. They were a good bunch. I spoke to Chris Hepplewhite. What impressed Chris was the longevity of the project and the endurance of the people involved. And it went on for, 14 years from proposal to launch? 16. He remembered that in the early years, NASA were hung up on the concept of smaller, lighter, and faster. Choose 2 out of 3. And a lot of effort was spent on trying to simplify the instrument without compromising the science. In the same vein, John Barnett had lobbied to get a complete year of lab calibration in Oxford, and he wanted that set in stone. And that would have been a perfectly sensible thing to do, but in the event, we had 3 months of mad panic. And after calibration, there was a quiet period when the spacecraft was being integrated, except there was one point when a cooler momentum balance mechanism broke. And it was all installed on the spacecraft at the time, and there was no way we were going to get it out and fixing it. And nevertheless, the cooler is still working well. Chris looked at it quite recently. There's very little vibration thanks to the control loop that John Barnett designed. Unfortunately, as you all know, after launch, there was a problem. And there was a lot of hard work from the NCAR team, especially. And we all know what was found. There was a piece of Kapton over the entrance aperture, and it was really very impressive in the way that John's team found a way of making useful atmospheric measurements through this little window at the side. And as a result, an enormous amount of science was done. I've picked out a random plot from the Hurdles website. I'm not going to say anything about what it means, I just picked it out because it looks pretty. Well, as a summary, it's all been great fun. And we've done some science. And I've appreciated over the years the connection between NCAR and Oxford. It's, from my personal point of view and from Oxford's point of view, it's been great. And I'd like to thank the organisers for inviting me to come and talk here. Thank you.
Thanks very much. Any comments or questions? Thanks. Nancy.
Yep. Sorry. I don't know why I chose to do that.
Okay. Okay. Thank you very much. Satellites have been obviously a very major focus of John's work, so I thought it'd be interesting to talk about remarkable growth of satellite capability, talk about URs, and indeed stratospheric ozone is a success story. And then since we're here, we can talk about satellite capability territory yet to be explored. We'll start off here with a graph I found on the web, and just like Clive, I was looking through things to find. And here's an interesting comparison: number of satellites from U.S., Russia, China, and other nations. I think 2 points here. Look at the one that says "Other," 472. It's just not United States, Russia, and China anymore. Our global community is a spacefaring community. And take a look at the orbits. You know, low Earth orbit, we're familiar with that. That's where we have a lot of the scientific stuff going on. Look at the geostationary. We're in a global community, and communications is important. And this is a geostationary component of it. Also, take a look at the military aspects for the U.S. It has a presence. I remember talking with John, and during the Cuban Missile Crisis, he was in Boston, and he got in his car and he started to drive west. Well, it was only a couple years later that the principal people in the military region figured out what really happened and how close we really came to annihilation. So we are lucky to be here, and we should celebrate that. When did satellites come about? Well, we have to go back to Isaac Newton. And I looked on the web and I tried to find this graph that has this little mountain top, and you have these projectiles, you know, and if you go fast enough from the top of the mountain, Newton said, well, you're going to orbit. So we have to go back 300 years. And I didn't find that graph. I did find this one here. And Newton invested in the South Sea Company. It had a financial bubble. And he said, I can calculate the movement of stars, but not the madness of men. So I think that's interesting. But I think we can say in unison, dear Mr. Newton, TIA CREP is a sounder investment. And may John and Ellen find out that TIA CREP will be give you many rewards down the road. Okay, innovation and persistence. John's work has been marked by this. Here's the paper again that we referred to earlier. In this talk, we'll give some perspective, some historical perspective, and we'll use 1970 as a date. The persistence aspects, Here we have a paper by John Hurdle's temperature profiles. Considering what happened to Hurdle's shortly after launch, the group was remarkable. They were persistent. And here we have a paper by John measuring temperature to a degree or so, considering what you started out with and where the group finally ended up measuring essentially the parameters that were advertised before launch. The aspect of persistence, I think this is a triumph of the human spirit. In the same way with Apollo 13, you know. So it's remarkable. Now, it's 1970 as a year to keep in mind. Pre-industrial CO2 was at 280. This is around 320. So from pre-industrial to 1970, when that paper on the limb sounding came about, that's 40 parts per million. From 70 to present, it's 80 parts per million. You know, things are increasing, and I call this galloping geophysics. In some sense, the horse is out of the barn. Another aspect of the horse being out of the barn having to do with the Arctic sea ice. 1970 is on the graph here, and you have to take this line and interpolate a little back. But the amount of change in this Arctic sea ice September 2014, it's 50%. So this is a major, you know, geophysical event. It's ongoing. It's going to be interesting to see where the story ends up. Now with ozone, you know, cell life, you go back 3.5 billion years. Cell life found a way of dealing with toxic oxygen. And so we have 500 million years ago, we have oxygen coming on the scene. Once you have oxygen, once you have ultraviolet, you have ozone. So the ozone appears roughly, you know, 500 million years ago. And our society found a way of possibly doing away with the ozone. Go back to the 1890s when the CFCs were invented. Midgley in the 1930s found out ways of producing the CFCs on an industrial scale. So you take 100 years, divide by 3.5 to the 9, whatever. That's a blink of cosmic time. You know, this is quite interesting because now we're in the situation because of international agreements that the CFCs, the CFC-11, the CFC-12, etc., they're phased out. Other chemicals are being used. And here's a graph from Rolando Garcia, Doug Henderson, Dan Marsh, published 2 years ago, having to do about the world avoided, and Paul Newman and others have talked about, well, what happens if you didn't have the international agreements? Well, the fact of the matter is 2050, which is only 13 years from now, ozone would essentially go off the cliff. So this has been avoided. And what I find it strange is that this is not celebrated to the extent that it probably should be, because if ozone did go off the cliff, that has a major impact on our civilization because of the biology. You know, it's quite strong there. Now, we mentioned about the Upper Atmosphere Research Satellite, the CLAYS experiment, measured CFC-12. In fact, the cross-sections that went into the satellite retrievals were measured here at NCAR and Jack Calvert's lab. Here we have the ground-based time series of CFC-12 from NOAA. And as you can see here, 2002, we're turning the corner. The CFC-12 is slowly decreasing. So this is a success story. The success story, in part, has to do with the aspects of, you know, the international agreements. And 2 weeks, was it a week or 2 weeks ago, President Obama met with the Chinese government officials, and maybe things will be moving in the direction down the road, still to be seen as far as CO2 is concerned. Now, what was remarkable about URs is that you had multiple experiments, multiple instruments that measured the variables in the system. So here, this is a diagram from Daniel Jacobs' book. And what we see here is that you have, when the temperatures get cold and you have polar stratospheric clouds, the inert chlorine is converted into the active chlorine. So you have measurements of HCl, chlorine, nitrate, sensors measuring ozone. So UARS was able to study the system, which I think was a very nice aspect of the UARS program. And there's no question about the reality of the science. You know, UARS nailed it. Now, polar stratospheric clouds, they were a surprise. They were a curiosity for most of the 20th century. And then Susan Solomon came up with the important realization that the heterogeneous chemistry on polar stratospheric clouds led to the Antarctic ozone hole. So that was a surprise. Now the question is, are there any other major surprises down the road for atmosphere, land, and ocean? And I think it's presumptuous to think that we've figured out everything. I have a feeling there will be some surprises. Now, in the UARS time frame, I think we need to thank Clive for this, that optimal estimation retrievals became the cultural norm in the atmospheric sciences. It's not yet the norm in the ocean color community. A few years down the road, there'll be a NASA satellite that will measure chlorophyll from space. They've done it previously, but they're going to do it again. Now, in the ocean color community, atmospheric correction, approximate radiative transfer is the norm. And I'm of the opinion for the 21st century, looking ahead, really Clive's way of doing the optimal estimation, a couple optimal estimation of atmosphere, aerosol, and chlorophyll is required. But it's going to take some evangelical efforts on our part to get the two communities to do this. We're also in for some changes down the road. This is not the most up-to-date A-train cartoon, but it makes the point. The remarkable aspect of having a half dozen or so satellites in the same polar orbit making coordinated measurements. At the recent CloudSat Calypso meeting that I attended, they talked about Calypso's fuel reserves. They're going down. So a year or two down the road, Calypso will be put into a lower orbit, so it doesn't do harm to the A-train, and then it goes back into the atmosphere. Well, Calypso goes down, CloudSat is going to follow, because Calypso and CloudSat are married together in many ways. Calypso measures smaller cloud particles, CloudSat larger ones, and they will follow. The recent addition to the A-train, the Orbiting Carbon Observatory, it will also follow, because OCO2 appreciates the information that Calypso and CloudSat makes as far as the vertical distribution of aerosol and clouds. So what we've gotten accustomed to, it's going to change. And the question is, what will we have in place 10 years from now? You know, and where is our nation heading? Where is Europe heading? What capability do we currently have now that we've kind of taken for granted? What will there be 10 years down the road? And I don't know what the answer is. Overall, though, I think human progress is possible. We mentioned about the aspects of the ozone, aspects of air quality, and we'll hear more about this in the afternoon. We go back to 1952, the London Great Smog event. London's cleaned up its act. Now you go to London, you go to the Tate Modern Museum. Well, that was the former Bankside power plant. So the societies are able to change. When I was a kid, our family in the Bay Area, my dad would get us in the car and we'd drive down to Los Angeles, make our consumer-related pilgrimage to Disneyland. And I remember the eyes would water because the air quality in the LA basin, it was just bad. And here's a picture of it. You can barely see that, you know, the LA City Hall, which is still there. Now it's much more visible. And year after year, the air quality in the LA area, it's gotten better and better. Even though, you know, the population is larger, but a lot of the controls on the automobiles, it's made a huge difference. Now, the question is, Great Britain's cleaned up its act. We're making a progress. If you're interested in bad air quality, now the story shifts to Asia. So here's a picture of a modern Chinese woman. She's with her handheld device, probably texting her friends, making sure that her knuckles down the road aren't going to work very well. And she has the surgical mask on because she's embedded in really bad air quality. Peter Nell's OMI experiment. You can see this from space. Here's the NO2 columns, and here we are over eastern China, and that's where the largest columns are. Whereas, the United States and in Europe, it's not as severe. So it'll be interesting to see what happens in Asia. Limitations of a current capability. Looking ahead, here's a picture from Mike King's MODIS instrument. It's become an icon. You see over the Ganges River basin all this dust and aerosol. It juts up against the Himalayas. In the Ganges River basin, where most of the population of India resides, you have these small domestic sources of aerosol, etc., and then it goes over to Bangladesh and out over the ocean. Well, this story here is also interesting because, talking about precise instrumentation, the GRACE satellite, there's actually two satellites in tandem, and they can measure slight differences in their relative separation as you go over changes in the mass gravity field. So if you do this on a month-by-month basis, you can notice that the aquifer of the Ganges River basin is slowly, changing. 1 week ago, the 60 Minutes show, I don't know how many of you saw it, but they had a segment. They talked about GRACE and they talked about California. California is in its 4th year of a severe drought, and GRACE can notice that in California the water table is going down. The agricultural industry is pumping out water that is now visible from space. So I guess where I'm leading to, the aspect of this aspect of aerosols and clouds, there's some limitations of what satellites can do. If you're interested in aerosol cloud interaction, you would really like to know what cloud condensation nuclei are, and there's no way yet to really measure that. So there's plenty of work to be done in the future, and if you can't measure it by satellite, it means you have to use other means in order to provide the observational links to be able to do better studies. Another limitation of current capability, by necessity, a lot of cloud screening is done. If you have a thick cloud, there's no way you're going to look underneath it. I do think there are situations where the cloudiness is maybe not so bad, and 3D radiated transfer in the future is going to be done to extract more accurate information from current and future data sets. And finally, an aspect has to do with multiple variable processes. We talked about the A-train and multiple sensors and all this capability. Well, if you dismantle that capability, a lot of these processes, it's going to be harder to study because you don't have the variables that are accessible. And if, for example, aerosol cloud interactions, the aerosol cloud indirect effects, you really need to consider cloud dynamics and aerosol microphysics. Not many studies do this. It would be good to measure this, the cloud vertical wind field in space. The Europeans will do that a few years down the road. They'll have a Doppler radar. But it'll be interesting to see what the United States can do in those regards. So in conclusion, I think definitely in the last couple of decades, there's been a lot of precise and remarkable work, and there's more precise and remarkable work to be done, and I'm looking forward to that. And with that, I thank you for your attention.
Thank you, Steve. Any comments or questions for Steve? Okay, we'll move on to our last talk of the morning. Let's see. Sean.
Well, before I start, I want to, first of all, thank everyone associated with this symposium. I want to thank especially Bill Randall and David Edwards from ACD and NESL for their support and encouragement. And Also, all the speakers for all the effort they've put in. Some of it misplaced, I can see, but and also for all of you for attending. I'm going to talk a little bit about some of the programs I've been involved with, and many of these plots you'll have seen before, so I can perhaps ramble a bit more and talk about anecdotes associated with them. This is based mostly on the programs I've been most involved with, and so not everything, I won't cover all the things that have been mentioned, but I'll, so it's somewhat, the topics are somewhat idiosyncratic, and also they depend a little bit on my memory, which I was going to say is a little bit shaky, but I can see not as shaky as some others. One of the, how this all began was when the question came up, well, how can we get a better attitude determination for satellites? Horizon sensing, or i.e. looking off at the horizon, or to use the astronomical term, the limb, had been used by U.S. satellites since 1958. And the local vertical is close to where the bisection of the angle to the two horizons. But the early results were noisy and unstable. It didn't work as well day and night. And so it was clear that you needed to avoid clouds, and a better approach was needed. So that meant to do better calculations of the expected signal. And now let's see, I think there's a pointer here. Yeah. Okay, so you imagine looking through the limb like this, and if you think of scanning down, this line of sight is going down to lower and lower altitudes, and you're looking through more and more of the atmosphere. So as you're looking at how much is emitted by the atmosphere, the more emitter, the bigger the signal, and so this shows say a down scan, and you're coming down, and the signal is going up. Eventually, you get to the point where the atmosphere is completely opaque, and then you become somewhat more sensitive to the temperature structure of the atmosphere. But you'll also notice that it's a very steep slope. Well, to calculate that these days would be fairly straightforward and trivial, but back in '66 and '67, when we started on this, computers were a lot slower. Transmittances were largely empirical. And for long paths and low pressures, as you have on something like this, those couldn't be reproduced in the lab, and so you had to make use of band models to help extrapolate those. And I should mention that Clive did a lot of work on some early band models. Sometimes taking care of the transmittances by overlapping gases could be tricky or uncertain, and Doppler broadening of line shapes needed to be taken into account. Of course, the refraction as you went through the atmosphere. And for most of this region, if you're looking at CO2, which we are here, departures from local thermodynamic equilibrium don't occur. But at that time, even getting good representative atmospheric data for a range of latitudes and seasons wasn't always easy. But eventually, over 1,000 profiles were calculated for the 15 micron bands of CO2, and duly printed in a thick report. We went on and found we could come up with an algorithm that would seem to give a fairly good way of getting a stable result. But I went on to spend the summer at NCAR, the first visit. It was a time when there was a lot of discussion of remote sounding and temperature structure in the atmosphere, work by, it'll come to me later tonight, I'm sure. But Dick Lindzen had recently solved a long-standing problem in atmospheric tides by including the negative modes with negative equivalent depths. And so it was a mathematically complete theory, and it's shown by this line here, but it disagreed with the rocket measurements. And then Conway-Leovy did a calculation where he said, well, suppose we didn't have any tidal motion, we just allowed for the atmosphere to be heated by the sun and cool off, and you got something with a diurnal variation like that. Well, I took that code and did some calculations and showed that if you calculated those radiance profiles and then looked at their diurnal variations, then for the tidal theory, you got a number like that. The observed was there, and Conway's value was there, but the resolution, which was mostly dominated by how well you could determine where you were pointing, was enough to show the difference. And so I said, well, this is a great way to resolve this problem, and I think we ought to make these measurements. Well, after many, it was not a straightforward process, but we went forward with the LRIR. One of the first things, it was nearly a showstopper, and we were in the office of the project scientist at Goddard, and told him what we needed in terms of pointing. And he said, we can't possibly do that. You're going to have to do better than that or you can't fly. So Fred House and I worked out a method, the so-called two-color method, which was a way of showing that we could determine where we were looking from our own measurements. There was also some cost problems. It looked like the cost was going to go over 3.3 million. It caused a lot of grief, and which is ludicrous now. But I spent a lot of time on the phone arguing that it was a good investment. They ought to go ahead and increase the amount that was allowed. Also, 4 kilobits per second data rate. That was looked like it was doable, but that was pushing the envelope a little bit. But obviously, along the way, a lot of on-the-job training for me. And here's the plot that Mike showed earlier. 68 kilogram mass, 27 watt power, very small by today's metrics, but looking at a single azimuth, 2 kilometer vertical resolution, and it was with this solid crayon, they calculated we'd have a 14-month lifetime, and it was, I guess, the first time I came across how inexact thermal modeling can be. We actually got 7 months. After watching the launch, which was from Vandenberg Air Force Base in the middle of the night, it was a deck of Stratus over the launch site. Rocket was ignited. For 3 or 4 seconds, we could see it, and it disappeared into the clouds, and that was about it. But then a few days later, went back to one of the data rooms at Goddard and watched some of the first results coming down and being printed out on strip charts. And one of the things we'd sort of expected that we'd see something that looked like this when you came down, and then when it turned around and went back up, you'd see the mirror image of it. Instead, we saw something that looked like this, had big bumps on it. Another bump went back up. And it looked like rabbit ears, but and we never simulated anything like that. But after a few minutes, we realized that we were seeing clouds, but it was a surprise from seeing those first data. Well, Bill showed one example of this. This was from a paper that we wrote in Science, showing one of our retrievals compared to a rocket sounding. And this is the statistics for 78 comparisons. And it showed agreement within about a degree, and most of them within the uncertainty. Also, an ozone sounding, and one or two of the rockets that made these measurements were launched by Ernie Hilsenrath, who was then launching chemical ozone sondes. One of these was launched from Alaska. And we had pretty good agreement there, too. There were only 4 comparisons, but they certainly were not bad, and I think you can explain some of these differences as just difference in time and exact location. So we proclaimed it a success, and the next thing, we began the collaboration with Jim Russell and the Langley group. And the first thing we thought of, well, let's expand the capabilities. Let's measure more species and look at multiple azimuths. And we first tried to develop an instrument like that, and one was actually built called the Limb Atmosphere Composition and Temperature Experiment. Built a balloon instrument to test the whole thing out, but the test was a fiasco. I'd launch the instrument dropped and banged on the ground a couple times before going up, and but we stayed up all night. We could see the balloon up above White Sands as the sun came up. But it turned out that the instrument was fatally flawed. There was some internal vignetting, so a lot of effort, but not much result. And then it turned out that building something like that for space would be too costly, over $10 million. So we ended up with the LIMS, which was basically an updated and improved LRIR. And as Clive mentioned, it was on the same platform with the Oxford SAMS. The differences, we now had 6 detectors and measuring in addition to ozone and water, NO2 and nitric acid, but otherwise very similar. And this just gives an example of some of the cross sections that resulted from LIMS. And I think Anne really said some nice things about LIMS, so I'll stop before I spoil that. The time flies. In the 80s, the Upper Atmosphere Research Satellite came along. Jim Russell and I proposed 2 IR limb scanners. One of them was the cooler that Mike mentioned. Oh, Mike didn't mention that on one of those, we spent some time at Goddard working on it, and we had somehow not taken care about our reservations in the hotel for that night. And we got to the hotel, and there were 2 rooms available. So I got one, and Bill got one, and Mike had a chance to sleep on the pool table. so he, and the quality of his work noticeably improved. The 2 instruments that were selected were Clay's and ISAMS. Clay's, for the first time, used an array detector, just a one-dimensional array, and a spectral scan with a set of tilting etalons. Again, solid neon to cool the detectors to about 20 Kelvin, and CO2 to prolong its life. Again, 1 azimuth, but now 13 species. As Mike and Clive mentioned, ISAMS had a mechanical cooler, had an ability to look at 2 azimuths and 9 species. And there was another limb scanner on there, the microwave limb sounder. Well, Clive has shown this and identified some of the people. I think there's an easier way to do it. After we got out of the bunny suits, there we are on the lawn, and you can see Steve and Clive and me and a lot of other people. I'm sure if you look at this picture, is also one of the ones on our website. You can recognize a lot of the people. But at this time, we knew that there was going to be an announcement for the Earth observing system. And so Jim Drummond came down and visited NCAR in the fall of 1987. And we got talking about how you could measure some of the gases in the troposphere, and especially CO. But Jim realized very quickly that we were relying on his knowledge and expertise with pressure modulators, pressure modulation cells, that you couldn't get enough couldn't move enough gas to get enough pressure change at the high pressures you need to look near the surface. So he went off and invented the length modulators, and we agreed that we'd collaborate, and he would be responsible for building the instrument in Canada, and we would develop the software to reduce the data. This is the sort of a schematic of the optics. Here's two length modulators and a pressure modulator, and the two sort of mirror image optical benches, which turned out to be a lifesaver. This is a picture of the instrument in there at the University of Toronto, where it was calibrated. The door is open. This is the part that looks toward the ground and gets the radiation coming up from the ground, and this is the look to space. And this is Jim just after Terra was launched. You can see the trail of the rocket behind him, and a successful launch. Well, you have to be, I wanted to get another picture of Terra. You have to be careful what happens when you just Google Terra. But it turns out that then if you look a little further, these are the Terra PIs, and you can see Jim and Mike King there at Vandenberg after the successful launch. I think probably this afternoon there will be a lot of discussion of or mention of Moffett results. So this is the showing some Hofmüller diagrams that Larry Lyjak and I did, showing the when you get into March and April, you can see these pulses of high CO coming across the Pacific. Since this is about the longitude of China, and this is the west coast of North America, you can see these pulses and you can track them across the Pacific. There's been a lot of work since then on this. I don't know that I've seen anything exactly like this, but certainly very graphic evidence of that's happening. And as has been mentioned, the team got the NCAR Scientific and Technical Award in 2006. Well, this is the Greek statue of Aura, the Nymph of the Cooling Breeze. And the statue was in the Palatine Museum in Rome, but somewhat later, Aura became the name of a spacecraft that happened to carry the hurdles along with MLS, OMI, and TESS. This is a picture of hurdles, and as has been mentioned, it was a collaboration between NCAR, Oxford, and a little later, University of Colorado. This is the wide aperture to be used to look at multiple azimuths. Now we've gotten into the modern era, and we're using mechanical coolers, and what else is, and this is just ready to go into the calibration chamber prior to being calibrated. Well, the collaboration with Oxford had a lot of side benefits. This was John Barnett and I signing the agreements for the US-UK cooperation on this. This is Joanne Lowe, who's the US project manager, and this is Martin something, and I kept forgotten the name of the UK program manager at that time. Martin Cordier, right, thank you. Then a lot of meetings in the Dobson room that some of you will know at Oxford. And in fact, in that cabinet is one of Dobson's early ozone spectrophotometers. Here we are on our way to lunch, as we've discussed before. And this is continuing work over dinner. I think this was at Brown's Restaurant, and a number of the team there discussing all the details that we've been going over during the day. This was John Barnett in the calibration chamber. John and the group at Oxford did a fantastic job. As we originally put a year in to do a complete calibration, But they developed a calibration facility that allowed a lot of remote operation, so we didn't have to break vacuum. We could put the instrument into this along with all the test equipment, and what we had thought would take a year, we did in a little over 2 months, and I think did a fantastic job. And John is gone, but he was a wonderful colleague. It was a pleasure to work with him, and we sorely miss him. Well, this is one of the things that we had hoped to do, to be able to make vertical scans at multiple azimuths and cover the globe with profiles like this. So we, as designed, we wanted to get something like a 1 kilometer vertical resolution, 10 species, 5 degrees longitude by 4 latitude, but programmable, and a Stirling cooler for long life. Well, what we actually got was our coverage is more like this innermost set of red dots. We got the 1 kilometer resolution, 9 species, less longitudinal resolution, and as Clive mentioned, the Stirling coolers still working, and we were defeated not only by the Kapton, but mostly the rotating chopper stopped on St. Patrick's Day in 1978. I'm sorry, 2008. Again, I'll mention this, which I think is one of the sort of a key or a very intriguing measurement, the Kelvin wave that Bill pointed out, symmetric about the equator. This is an equatorial Rossby wave. Again, these are symmetric about the equator and show good vertical resolution. And then the mixed Rossby gravity waves. And here, again, very fine vertical resolution and anti-symmetric about the equator. So that was a very nice addition. This is the Hurdles team at a meeting. John Barnett there and Chris Hepplewhite from Oxford. Mark Schobrel when he was the project scientist. A couple other people from Oxford there. This was in the atrium where we'll have the reception this evening. So then just a word about the future. I think potential limb scanning capabilities have increased rapidly in recent years, especially if you think about cooled large array detectors. You can have a resolution that will get many more species, many more azimuths, and keep at least the 1 kilometer, perhaps better vertical resolution. I think there's a recognition that some of the scientific questions related to the UTLS, especially stratospheric exchange, ozone recovery, and then the stratospheric influence on tropospheric weather and climate are really coming to the fore. And so there's a good match between the new and existing capabilities and these questions. So it looks like there's great promise for providing this information, and hopefully we'll have a chance to do that. So at that I'll stop and just say thank you again very much.
Thanks very much, John. Any hard questions for John?
What's next?
Next.